In this video, I will be explaining about the standardized value, also called the z-score. Let's start with the definition. For a given population with mean mu and standard deviation sigma, the z-score of a value x is the number of standard deviations the value is from the mean. In other words, the absolute value of z is the distance that the value x is from the mean using the standard deviation as a unit. To understand this better, it will be a good idea if we see an example. Assume that we have a sample from a population with mean mu equal 10 and standard deviation sigma equal 2. And that the histogram of this sample looks like this. The mean will be in some place around the center. Let's see that the mean is here, mean equal 10. So if we have a value, let's say 12, this 12 is 2 units from 10. But notice that this sigma is 2. So we say that there is 1 unit. If we use sigma as a unit, this 12 is 1 unit from 10. So we say that the z-score of this 12 is 1. So because there is only 1 sigma. So I'm going to type here that the z-score equal 1. But the definition of z-score is not complete yet. The z-score not only tells me what is the distance between the number and the mean, it also tells me in what position is the number respect to the mean. For example, at the other side, if we see here 1 unit, also 1 standard deviation at the other side, we have number 8. There is 1 sigma here, so there is the distance from 8 to 10 is again 1 sigma. But the z-score will be -1 because it's at the left, it's lower than 10. So will be the z-score equal -1. Let's see another number. For example, here, number 14, there are 4 units. This 14 is 4 units from 10. So it means that there are 2 standard deviations from here to here. So the z-score will be equal to 14. And at the other side, at this side, there will be number 6. And number 6 is again 2 units to 10. So number 6, the z-score for number z will be -2. So it's 2 units from 10 and it's also lower than 10. So it will be, the z-score will be -2. So the definition, the real definition of the z-score is this better. I think z will be x minus mu divided by sigma. And this will tell you a formula to compute the z-score. So for example here, 14 minus 10 equals 4. And you divide by sigma, that is 2. 4 divided by 2 equals 2. So the z-score for 14 will be 2. Then the z-score has its definition, the formula, x minus mu divided by sigma, where x is the original value. This is the value from which you are going to compute the z value. We have mu, that is the population mean, sigma, that is the population standard deviation, and z, that is the standard score. Let's see an example. The mean time that a certain model of bulb will last is 400 hours, with standard deviation equal to 50 hours. With this information, let's answer the following questions. Calculate the standardized value for a bulb that lasts 500 hours. Compute the standardized value for a bulb that lasts 340 hours. What bulbs have an absolute value of z equal 1? So what bulb has a distance to the mean equal to 1? And the other is what bulb has an absolute value of z less than 1? In other words, what bulbs have a distance to the mean less than number 1? The two first questions are very simple because just making a substitution solves the problem. For example, the first one, calculate the standardized value for a ball that lasts 500 hours. So the value of x is 500. So for the ball that lasts 500 hours, we have that z equal x minus mu over sigma. So it will be 500 minus 400 over 50. This 400 is the mean that is in the information of the problem, and this 50 is the standard deviation. That is 50 also in the information. So if you do that using your calculator, and the answer is 2. So the z-score for the 500 hours for each ball that lasts 500 hours, the z-score will be 2. For a ball, in the second question, if the ball lasts 340 hours, so we have that for this ball, z will be equal, again, x minus mu divided by sigma equal 340 minus 400 over 50. That is the standard deviation. So you do that in your calculator, and now the answer is negative. 340 minus 400 and divide by 50. The answer is negative 1.2. So these two questions were very simple. More interesting are the other two questions. For example, these questions. What balls have an absolute value of z equal to 1? In other words, what ball has a duration that is one standard deviation to the mean? Remember that the mean is 400 hours, the mean time. So to answer in these questions, what balls have an absolute value of z equal to 1? So we have this information. What is the absolute value of z? So in the equation we can make a substitution. Instead of writing z, so if we know that the absolute value of z equal 1, we can substitute here z by 1, or by a number that has an absolute value equal to 1. There is actually two numbers that have this absolute value, 1 and negative 1. So let's write this. For the balls with an absolute value of z equal 1, we have that this is plus or minus 1. So we have plus or minus 1 equal x minus 400 over 50. And we need to find the value of x. What balls has a value that is one standard deviation from the mean? So actually this expression defines two equations. One when we have negative 1, so negative 1 equal x minus 400 over 50, and another when we have 1, positive 1 at the values. Remember these two values has an absolute value equal 1. Okay, to solve this equation is easy. Just multiply both sides by 50. If you multiply this number by 50, you get negative 50 equal x minus 400. But you can you can add 400 both sides immediately. So this 400 appears at the other side plus 400. And the x is completely isolated, equal x. So first, cross multiply, and then move this 400 to the other side. It was negative this side, put it positive at the other side. You can think in this way, or you can think that you are multiplying both sides by 50, so you get minus 50, and the 50 disappears here. And then that you add 400 both sides. You get 0 here and 400 at the other side. Okay, that is the value, and then minus 50 plus 400, this is 350, so 350 equal x. You can do the same here. So multiply both sides by 50. So 50 times 1 is 50, and then 400, add 400 both sides. Here will appear 50 plus 400, and the x is isolated at the other side, equal x. So the other side, here you get 450. X equal 450. Good. So that means that the balls that last 350 or 450 hours, they have an absolute value of z equal 1. Now that we have answered question 3, it will be easy to answer question 4. And this question can be answered just making a graph. If we make a graph and we observe that 350 and 450 are two values that they are one unique to the mean is 400, every value that are between them will have a distance less than 1 unit, 1 standard deviation to the mean. So for that reason, the answer is the balls that last between 350 and 450 hours, they have an absolute value of z less than 1. This concludes my explanation of this z-score. Let's study now other topics related to this z-score. Let's speak about the Tchebyscheff theorem. This theorem says this, that regardless of how the data are distributed, at least 1 minus 1 over k squared of the values will fall within k standard deviations. And this will be true for each value of k that is greater or equal than 1. Remember that the number of standard deviation that a value is from the mean is called the z-value. So another way to write this is this. At least 1 minus 1 over k squared of the data set satisfies that the z-value will be between negative k and k. And this will be true for each value of k that is greater or equal than 1. For 1, for example, will be true. So I can say that at least 1 minus 1 over 1 square of the data set has a z-score within negative 1 and 1. That is between negative 1 and 1. Notice that until this moment, this theorem is not telling you too much. It's saying that at least 0%, and it's obvious that something must be at least 0%. The theorem starts to be important when you have a k greater than 1. So you have here 1.5, 1.2, or 2 or 3. For example, in the case of 2, the theorem will say that at least 1 minus 1 over 2 squared. Now it's 2 squared. And this is of the data set has a z-score that is between negative 2 and 2. So remember or notice that 1 minus 1 over 2 squared is 75%. You can see that this is 1 over 4, 2 squared is 4, 1 over 4, and 1 minus 1 over 4 is 3 over 4. 3 divided by 4 is 0.75, so it will be 75%. So the theorem is telling me that now at least 75% of the data set has a z-score within 2 standard deviations. So it will be between, the z-score will be between negative 2 and 2. So assuming that we have this distribution, and if we have this distribution have a mean. Let's say this is the mean 45 here, and they have a standard deviation. If we count 2 standard deviation to the left and 2 standard deviation to the right, what this theorem is telling me is that in all this area, that all this percentage will be the 75%. So the 75%, at least 75%, could be more. So at least 75% of the data will be between negative 2 standard deviation and 2 standard deviation. So that's what this theorem is telling me. So, and notice also that k appears twice in the theorems. Appears at the beginning when they say 1 minus 1 over k squared, and appears here again at the end. The z-value needs to be between negative k and k. So in case that k equal 3, we said at least 1 minus 1 over 3 squared. But 3 squared is 9. Yeah? So 1 divided by 9 is 0.11. So 1 minus 0.11 is 0.89. So 89% of the data set, at least 89% of the data set has a z-score that is between negative 3 and 3. So it means that if we put another standard deviation to the left, the proportion of data that are between these -3 and 3 standard deviations, or this proportion must be at least 89%. This could help me to know a little about a distribution that I have. For example, if we have this, a population of unknown Chevy that has a mean of 2,000 and a standard deviation of 150. We would like to compute, for example, I have this question. Find the minimum percentage of observations that are in the range 1700 to 2300. Find the minimum percentage of observations that are in the range of 1550 to 2450. And I also would like to know the maximum proportion of the observations that are above 2450. If we have three questions, these three questions, maybe the Tchebyscheff theorem can help me to answer the questions. Let's solve the first questions. Find the minimum percentage of observations that are in the range 1700 to 2300. It will be a good idea if we found the z-value of each of these values. So remember that the z-value, the Tschebyscheff theorems find the proportions of value that satisfies that the z-value will be between two values. So let's see if the Tchebyscheff theorem can help me with that. Let's find the z-value for 1700 and to 2300. So if x is 1700, then we have 1700 minus 2000, this is the mean, and divided by 150. So just remember the formula for the z-value or z-score. So in this case, we have 1700 minus 2000 and divided by 150. You can use your calculator for doing that, and I get -2. The Tchebyscheff theorem can help me if the z-score of each of these two values are the same but with different signs. For example, here, you notice that in the Tchebyscheff theorem appears -k and k. So these are the same value with different signs. So let's find the z-value of 2300. The z-value for 2300 is 2300 minus 2000, that is the mean, divided by 150, that is the standard deviation. And in this case, using my calculator, I notice the answer is 2. So the Tchebyscheff theorem helps me. Now I'm sure, because these two values are the same with different signs. I can type the Tchebyscheff theorem with the -2 here, and then will be 2 also here. So will be then 1 minus 2 square, and this is, I know that is 0.75. We already did it before, yeah? So I know that at least 75% of the data are within 1700 and 2300 in this range. To answer the second questions, so we are going to do the same, yes. So now the two values are 1550 and 2450. The Tchebyscheff theorem help me, or can help me, if the z-value of these two numbers are the same. So let's find the z-value of this and the z-value of the second one. So the z-value of 1550 will be, this is the formula of the z-score or z-value, so will be 1550 minus 2000 divided by 150. And this is, using my calculator, -3. I'm not sure yet if the Tchebyscheff theorem can help me, but it can help me if these two values, the next value, the z-value of 2450 is 3. And that's true, because z equal 2450 minus 2000 divided by 150. If I use my calculator, the answer is 3. So now I know that I can type the Tchebyscheff theorem. So will be here -3, z, and -3, and 3, sorry. And obviously here this number will be 1 minus 1 over 3 squared. So the percentage is at least 1 minus 1 over 3 squared, and this will be 0.89 or 89%. And that answer the second question. There is at least 89% of the observations are in this range. To know or to answer the next question, determine the maximum proportion of the observations that are above 2450. So we need just to observe that this 2450 is the same number that is here. If we make a sketch of the graph, whatever distribution, because the Tchebyscheff theorem works with whatever shape the distribution has. So for example, if we have this distribution, so I know if the mean is 2000, and whatever is the shape of the distribution, if the mean is 2000, and between 3 standard deviations that are between 1550 and 2450, there is the 89% of the data set. For that reason, outside of this region, so below this and above this, will be at most 11%. Obviously, if this could be 89%, all this area could be 89% or more, that means at least, if this is 89% or more, these things here outside of this region, maybe could be at the left and at the right, it will be at most 11%. And obviously, could be 89% or more, this could be 11% or less. So for that reason, the answer of the next question will be at most 11%. So determine the maximum proportion of the observation that are above 2450. It will be, the maximum will be 11%. So 11% of the data set, or at most 11% of the data set, is outside of the region between 1550 and 2450. Obviously, it could happen that there is nothing here. If there is nothing here, the whole thing will be here. Yeah. This is something that could happen. This is a thing that could happen. For that reason, we say that at most 11% of the data set are above 2450. That concludes my explanation about the Tschebyscheff theorem, and this is the way a Tschebyscheff theorem can help me to solve problems about proportion between two values. This need to be in such a way that when you compute the z-score, the two z-scores are the same number with different sign. In any other case, the Tschebyscheff theorem as is written cannot help you. Let's study now another topic related to the mean and the standard deviation. Let's speak now about the empirical rule. Assume that we have a data set of 200 values. This data set is coming from a population of mean 10 and a standard deviation equal 2. And I made the histogram. When I constructed the histogram, it looks like a usual histogram. In some way, there is a symmetry here because the rectangles in both ends are shorter, and the one in the middle is higher than the others. Yes? In some ways, it's not completely symmetric, but it is in some way. Even if I do that, if I notice that, I will be thinking maybe the histogram for the whole population will be bell-shaped. It's like it has the shape of a bell. Start from the lowest point, go higher into the middle, and then go down again to the right. To check if this histogram is actually coming from a population that is bell-shaped, what I did was compute the z-score of each value and then find what is the amount of value that falls within 1 standard deviation or 2 standard deviation or 3 standard deviation. So finding the z-score is going to help me with that. Remember, the z-score is the distance between the distance in a standard deviation between the value and the mean. So let's do that. So obviously, because the standard deviation is 2 and the mean is 10, 10 minus 2 to be within 1 standard deviation is to be in the interval between 8 to under 12. Of course, because 10 minus 2 is 8, 10 plus 2 is 12. To be between 2 standard deviations, to be within 2 standard deviations, so 2 standard deviation will be 4. 10 minus 4 equals 6. 10 plus 4 equals 14. So to be within 2 standard deviation is actually to be in the interval 6, 14. And to be in the interval within 3 standard deviation is to be in the interval 4 to under 16. So if you notice, 10 minus 6, 3 standard deviation is 6. 10 minus 6 equals 4. 10 plus 6 equals 16. So I computed actually the number of elements that are in each of these. So for example, between 8 and 12, there are 141. I use the function count in cell. 190, there are between 6 and 14. And between 4 and 16, there are 199. Almost all the data, because there are 200 data. In percent, this will be the 70.5%, this will be the 95%, and this will be the 99.5%. And when I see this, now I'm almost sure that this is coming from a bell-shaped distribution. But why I know now that this is coming from a population that has a bell-shaped distribution? Because I know the empirical rule, and the empirical rules say that these percentages are like this. So if the population has a distribution that is bell-shaped, then approximately 68% of the data set has a z-score that is between -1 and 1. So 68% of the data set are within 1 standard deviation from the mean. 95% of the data, almost 95% of the data, so all of these are approximations, has a z-score that is between -2 or 2. So 95% or around 95% of the data falls within 2 standard deviations. And almost all the data, so almost 100% of the data set, has a z-score between -3 and 3. So here you see in the graph that almost all the data are between the 3 standard deviations. Here in the middle you can see the mean. That could help me to answer some questions about the proportions of data between values. For example, the mean time that a certain model of ball will last is 400 hours, with a standard deviation equal to 50 hours. Assume that the distribution is bell-shaped. Now let's assume that this distribution is bell-shaped. And we have these questions. What percentage of balls could be expected to last between 350 and 450 hours? What percentage of ball could be expected to last between 300 and 500 hours? And finally, what percentage of ball could be expected to last longer than 500 hours? And observe now that this is similar to the Tchebyscheff theorem. These two numbers need to be the same. Yeah? But now we don't have at least, now we have an approximation. And the other thing is that the empirical rule only uses these three numbers, 1, 2, and 3. The other difference with the Tschebyscheff theorem is that Tschebyscheff theorem could use whatever k here that is bigger than 1. So it could be 1.2, 1.3 in the Tchebyscheff theorem. But here in the empirical rule, just these three propositions are true so far. Because maybe later in this course, we will be speaking more about this empirical rule. We will be extending this to other numbers. But so far, we can use it with these three numbers, 1, 2, and 3. Okay, if that is the case, let's solve this problem. Let's answer the first question. What percentage of balls could be expected to last between 350 and 450? Again, as you were doing with the Tchebyscheff theorem, compute the z-score. If you compute the z-score of these two values and check if these two z-scores are the same. If you do that, let's see the z-score for 350. So will be x minus mu. In this case, the mu is 400 and the standard deviation is 50. So will be 350 minus 400 divided by 50. And I get -1. The other number needs to be 1 to be sure that I can use the empirical rule. Let's see. Z for the 450 will be 450 minus 400 divided by 50. And this will be equal to 1, exactly. Now we can answer immediately. If this is between -1 and 1, so if this falls between 350 and 450, it's equivalent to say that the z-score is between -1 and 1. And that means that we have the 68% of the data, almost the 68% of the data. So that will be the percentage between these two numbers. In the case of the second questions, what percentage of ball could be expected to last between 300 and 500 hours? So in this case, we have that again we compute the z value of 300. That will be 300 minus 400 over 50, and this is -2. And we need to check that the other z-score need to be 2. So if I do that, z equal, the other number is 500, 500 minus 400 divided by 50. And this is exactly equal to. So now I know that approximately 95% of the data will be between these two numbers. Have this z-score, so will be between these two numbers. And finally, what percent of balls could be expected to last longer than 500 hours? So in this case, we have this question, and we have that our distribution is completely symmetric. Now, this is different to the Tschebyscheff theorem that could be whatever shape, yeah? But in this case, need to be symmetric and bell-shaped. Now we know that the percentage of data that falls within 300 and 500 is 95%. If this is 95%, the amount of data that falls outside of this region, so it means below 300 and above 500, will be 5%. And because the question is what percentage of balls could be expected to last longer than 500 hours, then here will be just half of the 5%. So the answer will be just 2.5%. And that answers question 3. With this, I finish my explanation about the empirical rule and about all this topic related to the z-score. Thank you.